In this video, we're going to talk about center of mass. Now, center of mass is a pretty intuitive idea. If you have an object that is symmetrical, like a sphere, then at its center is the center of mass. And this symbol right here means center of mass. But if we have something that is a bit irregular, like say a hammer, this is going to be a terrible looking hammer. Oh, wait, that's not that bad. Then there's going to be more mass situated at the top, where all of that metal is going to be, and so we would expect the center of mass to be somewhere higher up on that object. You can also have something like a ring that has a really big hole in it. This object is symmetrical, and so the center of mass will be in the center even though it's not touching any physical part of the object. Now, all of these use the same equation to find the location or the position of the center of mass, and that is that the position of the center of mass, or xcm, is going to be the sum, so sigma, of every product of mass and position divided by the sum of all of the masses. Let's do some example problems to help us understand this equation. In this example, we have three spherical masses that are arranged as shown. If MA equals 3 kilograms and MB equals 1 kilogram, what mass does sucka MC need to be so that the center of mass of the whole system is at the origin? So the origin is, in the middle. There's going to be 0 there. And so what this is telling me right here, the center of mass is at the origin, that's telling me that the center of mass is equal to 0. And this whole thing right here is telling me that I need to figure out what the mass of C is going to be, and I'm going to use the number line to give me the locations. So let's use our equation. X center of mass is sigma mx over sigma m, and let's add up all of these different mass and locations. First, we're going to get MA times a location, and in this case, I don't have any units for the location, so I'm just going to use a number. MA is at 1, 2, 3, 4, negative 4. Then I'm going to add the next mass, which is mass B, and its location is at 1, positive 2. Then, of course, I've got mass C, or sucka MC, and I want to figure out what that is. That's why I'm going to write it as MC, and there's a location of 1, 2, 3, 4, positive 5. All of that is going to get divided by the total mass, MA plus MB plus MC. Okay, now if I think about this problem by entering in these masses, I'm going to ignore the units for now, but for mass A, I'm going to put in 3. And for mass 2, or MB, I've got a 1. And I could combine these two and say 4 plus MC, but there's a really interesting trick to this problem, and that is that the center of mass is equal to 0. And so if I set this whole equation equal to 0, then I don't really care about this bottom term because I can multiply both sides by that whole thing and it will disappear into 0. So that's what I'm going to do here with the magic of an eraser. Bam, it's gone. Okay. So now I have an equation where all I'm trying to do is simplify to find MC. So let's do that. 0 equals 3 times negative 4 is negative 12 plus 2 plus MC. I'm going to call that 5 MC. I like to put the numbers out front. And so that's going to give me a negative 10 plus 5 MC. And I think you can see where to go from here. If we want to solve for MC, then all we're going to do is add 10 to both sides and then divide by 5. And that's going to give us that sucka MC is equal to 10 over 5, or 2. And again, we won't have any units because this is on a number line, and so that's the x-coordinate we're looking for. Sometimes you won't be given numbers in a problem like this, though, and you'll have to do things symbolically. Let's try an example. The center of planet X is a distance d away from the center of planet Y God Y. Planet X is 3 times more massive. Where is the center of mass located relative to planet X in terms of d? So this is a classic center of mass problem. Let's draw planet X. It's much bigger. And over here we'll draw planet Y God Y. And it gives us this information about the times more massive. Planet X is 3 times more massive. So what that's a call to do is to say, okay, planet Y, let's just call that mass M. And so the mass of planet X is going to be 3m. Okay, good. And now these are a distance d away. It's the distance that their centers are. And when it comes to center of mass problems, you kind of need a number line where there's a 0 and some extended length. Now, what we have is not a number, it's a letter. So we're going to say that 0 is right here at planet X, and planet Y is a distance d away. We could do it the other way or put 0 in the middle, but this is going to be how I choose to solve this problem because it's going to simplify our center of mass equation pretty well. So we've got mx over m. And so we'll do the mass of planet X first, 3m times its position. Oh, its position is 0, so maybe you see why that's a good idea. Then the mass of planet Y times its position, which is d. And I divide that whole thing by the total mass, which is 3m plus m. Obviously, there are some simplifications we can make here. 3m times 0 is 0, so I've got md on top. And on the bottom, I'm going to have 4m. And voila, the m's cancel out, and I get that the center of mass of this system is d over 4. And so if I was to divide this line into 4 sections, this one would be d over 4, then that is where the center of mass of this system of the two planets is located. And notice we didn't actually have many numbers in this problem. We're not getting an actual distance. It's kind of a fraction of some initial distance given to us as a letter. Let's do another example of this. You are at the end of a diving board of length L looming into the abyss. You are 4 times the mass of the diving board. Whoa. Where is the center of mass located in terms of L? Okay, so in this problem, I'm going to draw a diving board, but I'm terrible at drawing, so I'm going to draw just a rod or a board or something like that. And it's going to have a length of L, so I'm going to put 0 on the end and L here on the right to represent it kind of as a number line. You are 4 times as massive as this bar. That means that this rod or bar or whatever board has a mass of M. I'm going to put a little squiggly line to indicate that. And you're at the very end, looming into the abyss. How did you get here? We may never know. Anyway, you're kind of big, and so you are 4 times bigger, or 4m, compared to the board. Now, with this information, I can write a center of mass equation. I've got the mass of the board, and I just need to come up with a position for that board. And then I'll have the mass of you, 4m, times your location. Well, you're located at a distance or a position of L. But let's come back to this question of, well, where is the board located? Because the board is located everywhere from 0 to L. Well, in this case, when you don't have a point in space, you actually have an extended object, then the position that you put in here is the position of that object's center of mass. Now, assuming that this diving board has a uniform mass density, meaning it has the same amount of mass along the entire length, like it's not a hammer, then we can say the middle is where the center of mass is located for that board. That is going to be written as L over 2. And so I can put L over 2 in my equation here. And I will get mL over 2. Oh, I forgot to do the bottom. All of that's going to be over m plus 4m. So on this equation, I'm going to have mL over 2 plus 4ml, and then all of that is going to be divided by 5m. All right, fractions, they come up in center of mass pretty often. So here I have an interesting looking fraction. But basically, on the top, I'm going to have like 4.5 ml over 5. M, the m's are canceling. And 4.5 over 5, I can actually scale that up into a fraction pretty easily. Just multiply both by 2, so 9 over 10 L. And that is the location of the center of mass for this system, which makes sense because if I divided this board up into 10 parts and I was 1/10 away from the edge, then that is the center of mass, not for the board, but for the whole system. Right? Center of mass SYS or something like that. Who knows? Okay. Now, sometimes you are going to have to use this problem in 2 dimensions. So let's look at that. 3 spheres are arranged as shown. The mass of MA is half the mass of MB, and the mass of MC is 4 times the mass of MA. Don't like that. What are the coordinates for the center of mass of the system? Okay, so right away, let's deal with this crazy logic sentence right here. what is it telling me? Well, it's saying the mass of MA is, so MA equals half the mass of MB. Okay, MB over 2. Well, what I might do in this case is say, how about we just say MB is actually equal to M? And so then I can say that MA is M over 2. And then MC says is 4 times the mass of MA. So if I take this and multiply it by 4, I'm going to get 4 over 2, or just 2M. Okay, having all of these masses with the same term, M, in them is going to allow us to cancel out later like we've done in some of the other problems. Okay, so now let's deal with the two-dimensionalness, or whatever dimensionality, that this problem presents. We know what to do with the center of mass. Okay, we're going to add the product of all, or sorry, the sum of all the products of mass and position and divide by the sum of all the masses. There are 3 objects, so this is going to give me mass of A, which I'll use this. I'm just going to go ahead and jump right to mass of A is M over 2. So what's its location? MA, its x position is 1, negative 2. Okay, so negative 2. Then for B, I have a mass of M. And B is, it's at 0. There's no x location for B. That's good. And C, I've got 2M. And it looks like it's located at 1, 2, 3, 4, positive 4 position. Okay, so all of that gets divided by a total mass of M plus 2M is 3M plus M over 2. I'll write that out. We've got M over 2 plus M plus 2M. And let's do some simplifying. Okay, so first of all, on top, I'm going to get M over 2 times negative 2. The 2's cancel. And I just have negative M. M times 0 is 0 plus 2M times 4, I'm going to write that as 8M. Okay, and then this is divided by M over 2 plus M, so 3.5M. Well, I'm going to write that as 7 halves M. And then on top, this is going to be, there's a reason why I wanted that 7. This is going to be a negative M plus 8M, so negative 7M. And then I divide that by 7 halves M. And 2 things cancel, the 7 and the M's. And this 2 comes right back up on top, and we're going to get a negative 2 for our answer. Okay, so we know that that is the x-coordinate. Man, that was a lot of math, but we did it. Good job. Go you. Okay, so somewhere over here is going to be the location of the center of mass. Well, how do I find the y-coordinate? Well, you may have already guessed it. You just do the same thing, but you use y's instead of x's. That would be y's. Oh, good. Okay, so we're going to run out of room here. So what do we have for the y's? Well, for y, we've got M over 2 for A, and its y location is 1, 2, 3, so a positive 3. Then we have for B a mass of M, and it does have a y location of negative 2. So times negative 2. Then I'm going to add that C term, which is a mass of 2M, and it goes up a y of 1. And then all of that gets divided by the 7 halves M. Okay, now before we solve this, let me go back and make a little bit of a correction. Negative M plus 8M, that's positive. So this is going to give us a positive answer. I'm not sure what I was doing there. But anyway, okay, back to y. How do we simplify all of this stuff? Well, there are going to be a lot of terms. Essentially, we're going to get 3 halves M minus 2M plus 2M all over 7 halves M. Kind of nice because this negative 2 and that positive 2 is going to cancel. And you know what? I'm actually going to bring this over here because I need some space. So I've got 3 halves M. I'm going to write that as 3M over 2. And then instead of trying to divide by this fraction, I'm going to multiply by the inverse. So 7M over 2. Sorry, I said inverse. So 2 over 7m. And then the m's will cancel, the 2's will cancel, and I'll be left with 3/7. Okay, so my coordinates are going to be positive 2, so 1, 2, and then about 1/2 almost right about there at 2,3/7. Okay, let's take a look at one last example where we're going to have a two-dimensional center of mass problem, but this time it's going to be symbolic. You make a weird boomerang-looking thing by connecting two sticks of the same length L at a right angle. That's kind of the picture here. If you were to hang this object by point P and allow it to come to rest, how's it hanging? So, let's think about each of these as having a length of L. And since we kind of want to think of this as an origin, let's put 0 and 0 here, and then L and L here. And we'll use that to conceptualize the center of mass for both the x and the y direction. Before we do that, though, we have to realize that each of these is really like its own bar, and they're uniform, so the center of mass is at L/2. Just like that for each bar. Armed with that information, we can now solve these problems. So in the x direction, I'm only going to have mass, when we should say that these bars have the same mass because they're the same two sticks. Just to clarify. So the only x center of mass that we have is going to be this one. And so we'll have m times L/2. And then that is going to be divided by the total mass. Well, the total mass is actually 2 of these bars, so it's 2m. Even though this bar is not contributing anything in the x direction, we still have to include the mass in our mass distribution, and this you'll see it makes a big difference. And so what we're going to get, the m's cancel, and we'll get 1/4 L, or L/4. Okay, so that would be right about here. Okay, for the y center of mass then, we would have, again, an m, and the y center of mass location is at L/2, and there are no other y values. So we then divide that by 2m. M cancel out, and we get the same center of mass, L/4, which would be right about here. L/4, L/4. Okay, so the center of mass of the system, and it's approximate, right, is towards that pointy part of the boomerang. So if you let something hang and balance around a pivot point, then you are going to have a center line, and the center of mass will go through that center of line. I'm going to get rid of this work right here, and let's draw what would this look like. Well, basically, if we took this point P and put a string on it and let us, hang the object there, then there would be a vertical line. And after this object has swung and calmed down, then there would be a center of mass that's in line with that pivot point P. And judging from this picture, if I draw a line between the center of mass and point P, then I can kind of get an idea of what it's going to look like if I try to draw this vertically. There's going to be a little bit of mass that crosses over that line. This is a terrible drawing, but you get the idea. So sometimes on really tough physics questions, you'll be asked to identify where or how would this object look if it was hung, and you would want to look at where the center of mass is and draw a straight line for that. Without doing any math, I could probably just look at this and say, I bet most of the mass is centered somewhere in here, and not really have to do any of this algebra and all that stuff, and kind of just identify that that's what it would look like. Okay, so in this video, we covered all kinds of crazy things about center of mass in 1 and 2 dimension, and how to find the positions of the center of mass or work with those two equations. And now this video is done.